In this video, we are going to evaluate a few more limits that are going to involve a bit of algebraic manipulation. Now, the general rule of thumb when approaching a limit is to first check, can we plug in the value? So for example, it's a limit as x approaches 0, so our maybe natural first instinct is, can we just simply replace each and every x with a 0? Well, unfortunately here we cannot do so because this expression is undefined at x equals 0. And since we cannot simply plug in x equals 0, we don't want to apply our limit laws yet. So instead what we will do is use some type of algebraic manipulation. And the algebraic manipulation that I think will be most useful here is to just combine into a single fraction. So we need to find a common denominator. So I'm going to take the first term, 1 over x, and multiply it by x plus 1 over x plus 1. And that will give the function that we are taking the limit of the common denominator, x over x times x plus 1. And what we will have in the numerator would be the x plus 1 from the first term and minus 1 coming from the second term. So now, plus 1 minus 1 cancels, and the only thing that we are left with in the top is an x, and that's very nicely going to cancel off with the x that we have in the denominator. And at this point, we are in an ideal situation. We have the limit of a rational function, so we can simply apply our substitution property. And the substitution property tells us in order to evaluate this limit, we can plug in the value 0 as long as the function is defined, which it is here, and the value of this limit is simply the number 1. So once again, the big observation is that if we cannot directly apply our limit laws, we first do some type of algebraic manipulation / simplification and get it to the point where we can apply our limit laws. So another very similar type of example. To evaluate this limit, my first instinct is, can I plug in x equals 1? But if I plug in x equals 1, the denominator would be 0, and that would be undefined. So before using the limit laws, I am first going to need to do some algebraic manipulation. And in order to use some algebraic manipulation, we're going to use a very common technique. When we have limits of this form, especially terms that involve a square root plus or minus something else, and I cannot simply plug in the number, we like to multiply by the conjugate over the conjugate. So looking at the square root term in the bottom, its conjugate will be the square root x plus 1. And one thing that we can do to algebraically manipulate is to multiply by 1. And here we've just multiplied by 1 in a fancy way, the conjugate over the conjugate, and that's going to hopefully simplify this expression. And let me just to the side give you an idea of why this is useful. If we have an expression of the form a plus b, then its conjugate would be a minus b. And when you multiply them together, you get a squared minus b squared. It's the difference of squares formula. So if we FOIL out what we have in the bottom, you're going to get the first term, the a squared, which would just be an x, and you're going to subtract away from that the second term, the b squared, which would be 1. In the top, you have x minus 1 times the square root of x plus 1. So the x minus 1 in the top and the bottom cancel, and we are now left with a limit as x approaches 1 of the square root of x plus 1. Now this is not a polynomial or a rational function because of the square root, so we cannot apply the substitution property, but we can apply our limit laws. We take the limit of the first plus the limit of the second. The first is a limit of the square root, so we can go ahead and plug the limit inside the square root. And the limit of a constant is always at constant. So square root 1 plus 1, which is the number 2. In this example, we will evaluate the one-sided limit. Now, the observation to make is that all of the limit laws we've previously encountered can be applied directly to one-sided limits. Additionally, looking at the expression we have, the square root of 3 plus x, whatever we plug in for x has to be larger than minus 3, and we're approaching minus 3 from the right. So we are going to stay larger than minus 3. The function is not a polynomial or rational function, which means we need to apply our limit laws. So the limit as we approach minus 3 from the right of the square root of 3 plus x, divide it by the limit as x approaches minus 3 from the right of x. So by our second limit law, the limit in the bottom is going to be the number minus 3. And in the top, we can take the limit and plug it inside the square root. So this will be the square root of the limit as x approaches minus 3 from the right of the quantity 3 plus x. And now that we have applied our limit laws, the observation to make is this resulting limit is the limit of a polynomial, which means that we can use the substitution property. And the substitution property tells us that we can simply replace that x with a minus 3. So it's a square root of 3 minus 3, so the square root of 0 over minus 3, which is the number 0. So let's evaluate one more one-sided limit. And here, note I can't just plug in 0 because we'd end up with 0 over 0, which is an undefined quantity. But what I can do is think about how we have defined the square root function previously. We defined the square root function as a piecewise defined function. If you plug in a positive number or 0, you get that number out. If you plug in a negative number, you get out the opposite of it. So remember the graph of the absolute value. To the left of 0, you're looking at the graph of the line y equals minus x. To the right of 0, the graph of the line y equals x. So when we evaluate the above limit, we're thinking about approaching 0 from the left. So when we're approaching 0 from the left, the function that we need to think about is y equals minus x. So this becomes the limit as x approaches 0 from the left of x divided by minus x. And the big reason, once again, is because if you have a negative input to the absolute value, you're dealing with minus x as the output. X over minus x cancels, and this leaves us the limit as x approaches 0 from the left of the constant function minus 1. And the limit of a constant is that constant.